Okay. So let's perform the second part of today's seminar. Well, the second part are just more standard content, and well, let's begin. So I will conclude this seminar at LSC reduction formula, I think. So let's see. Using such a field theory, this field operator, we can just build the Lagrangian formulation. Lagrangian. Okay. First, we can perform a time derivative of this field operator and obtain so-called pi x to 0. Pi x equals to pi d3p over 2 pi to the power 2ep times ep a dagger eipx minus a minus ipx. Okay, and using the expression of pi and phi, we can easily check that actually the commute they satisfy the commutator relations. It's just some very easy check. Y in the same time equals to pi x. Okay, I think I have unmuted me. No problem. Okay. S0 in the at the same time equals to 0, and the commutator between phi x and pi y are just I data x minus y. Yeah, we can easily check those relation, and based on this, we can say we can state that this pi x is just the conjugate momentum or canonical momentum of our field operator. I noticed an interesting fact that these two expressions are both the combination of the annihilation and creation operator A and A dagger. So we can invert them to obtain the expression for A and A dagger in terms of pi and phi. And the expressions are very useful later. Yes, we can invert, but I and phi to obtain the expression of A dagger and A. That's A 3x px pi x plus ip phi x. And for A, was positive I d square x eipx pi x minus I ep phi x. Okay. Okay. And in the second quantization theory, or the just the quantum mechanics, the standard quantum mechanics, we know the Hamiltonian can be just written as, or based on those principles, we can introduce such a definition of the Hamiltonian. 3p over p ep ap dagger AP, yes, plus VEP. Yeah. Right. And this V is just the volume of our system. And this definition is very easily to understand. It's very easily to understand in the intuitive way because you just count how many quanta and just count them and we add them up or integrate. We obtain such a formula of the Hamiltonian. It's very easily to understand. And using the expression for A and A dagger, we have just obtained, we can rewrite this expression as 3 1 half I square 1 half nabla phi x square at 1 half m square phi square. Yeah. And now how can we obtain the Lagrangian? Well, we just introduce two restrictions. First, we know that the Lagrangian theory, the conjugate momentums are defined by delta L, delta partial 0 phi x. And second, we know the relation between the Hamiltonian and the Lagrangian equals to x partial 0 phi x minus L. Okay, and using these two requirements, we can just obtain the Lagrangian density immediately. Square 1 half partial mu phi x partial mu phi x minus 1 half m square phi square. Okay, and similarly the action dx0 L. Yeah. And notice that we can just use the Euler-Lagrangian equation to revive the Klein-Gaussian equations. It's really simple. Just use I think I'd better write it down. EL equations, which is partial L. Maybe I should use delta R anyway. Partial L, partial L, partial mu. Fine. Yeah, using such an EL equation, we can immediately revive the Klein-Gaussian equation. Just a self-consistent chart. And then interesting stuff in this Lagrangian formulation is just the Noether theory. So if we perform a small change to the phi x, to the field phi x, make phi x to phi x plus a little epsilon per psi x. If we assume the Lagrangian will not change, or the Lagrangian is unchanged, delta L, we can obtain partial phi epsilon per psi plus partial L partial mu phi epsilon partial mu capital per psi. No, not this one. It's a mistake. Partial mu. Yeah. Okay. Using the Euler-Lagrangian equations, we can just obtain partial mu, partial L, partial mu phi epsilon per psi plus partial L, partial mu phi epsilon partial mu per psi. And finally, we obtain epsilon partial mu partial L partial mu phi per psi. Yes, and we know it vanished, right? So we can just define this one to this current to be nozzle current J mu. It's called nozzle current, which is conserved during such a little transformation. Okay, it's not a theory. Okay, so much for this. And up to now, all we have talked about is the free scalar field. But in physical reality, we must encounter the interacting system. So we must discuss the interacting scalar particles next. Scalar particles. Okay. So how do we obtain the interacting scalar particles? Well, we make an addition term in the Hamiltonian H. I think it's the easiest way to obtain an interacting system. Now, what's the restriction of this addition term? Well, because this Hamiltonian will generate the time evolution operator, so we require such an addition terms to be Hermitian. Hermitian, no. Hermitian addition terms. The reason is that the time evolution operator must be unitary. Terms. Okay, and the most simple way to introduce is H interaction lambda over n factor d3x by n x. Okay, and this one is called the coupling constant. Coupling constant. And if we require the if we consider the specific example for n equals 4, we can just write down the Hamiltonian and Lagrangian immediately, such as over 1/2 pi f squared plus 1/2 lambda phi x squared plus 1/2 m squared phi squared plus lambda over 4 factor pi 4x. Yes, and Lagrangian. Mu phi x. Mu phi x. Let me check. Yeah. Okay, great. Minus 1/2 m squared phi squared minus lambda over 4 factor phi 4x. And similar and correspondingly, we obtain the non-linear or the inhomogeneous KG equation, which is non-linear. Square phi x plus lambda over 6 phi to 3 equals 0. Yeah. It's the inhomogeneous plane Gaussian equation. Now, how can we deal with such a interacting system? Well, we can build it. We can just build the interacting system from a free field. How can we do it? We can assume this coupling constant lambda. This coupling constant lambda. We'll assume it is slowly time dependent. And we'll assume for in the far future and far past, we will obtain the free field theory. X0 tends to until negative infinity, lambda equals to 0, which means lambda tends to 0 adiabatically. And we can, and based on such assumption, we can construct the interacting system using our free theory. Because in these 2 points, actually we have free theory. And we can construct the interacting theory based on it. So how can we do it? First, we can just introduce the in and out states. Wait. No. Let me check. Okay, let's continue. Now, not in and out state. We can just first introduce the in and out free field operator. Yeah. Taking such a limit, x0 to minus infinity, such phi x. Notice here, this phi x is the interacting field, not free field. But if we take this limit, we obtain phi in x. And this one is a free field operator. Yeah, and we can write it down again. 2.3 2EP A dagger P in. Notice here in IPX plus A P in minus IPX. Okay. So how can we express such a relation in a transformation viewpoint or perspective? Well, we can just introduce the time evolution operator to express it. Phi x to u infinity x0 phi in x u x0 minus infinity. This u is just the time evolution operator. Satisfying the following properties. Partial t u t prime equals to I 3x. Yeah. Find interaction, phi in x. And let me check it. No. Yes. UTT prime. Okay, no problem. And of course, UTT equals to identity. Okay. So how do we solve such a time evolution operator? A naive solution is just put an exponential solution. However, it is not correct because we don't know. We don't know that because in different time we don't know this term phi in x. itself commutate. We don't know whether it can whether it commutate with itself at a different time t or not. So we cannot just make a naive solution using the exponential function. So the correct way to write down the function is to using the time order exponential function ut2 t1 was this capital T means time ordered. T1, T2, dx, d4. Yes, and this time orders will make this argument from left to right become the decreasing time argument. T argument. For example, yes. For example, we can just expand it to sit t0 t d tau a tau equals to 1 plus 0 to tau d tau 1 a tau 1 plus 0 to tau d tau 1 0 to tau 1 d tau 2 a tau 1 a tau 2 plus blah, blah. Notice that from left to right we have the decreasing time argument. Okay, and using such a solution we can easily check that it satisfies all the properties we require. T capital T time ordered exponential 0 to t tau a tau to at time ordered exponential 0 to t d tau a tau. Yeah, it can be checked very easily. And obviously other two properties u t3 t2 t1 equals to t3 t2 u t2 t1. Yeah, for arbitrary t2 we have such a relation, and obviously in the inverse transformation, the inverse evolution t1 t2 equals to u inverse to t2 t1 equals to u dagger t2 t1, because it's a unitary operator, obviously. Okay, and using such a time evolution to express the interaction field phi x, we can obtain the following equation from the inhomogeneous Klein-Gaussian equation. Okay, yeah, lambda over 4 over 6 phi 3x. We can just substitute this equation, and we will know. We can just obtain u minus infinity x0 partial square m square phi in x u x0 minus infinity. Okay. And now we can construct the so-called in and out states. Let me check. Okay. Out states. Introduce the ground states for the far past, the in states. 0 in is the ground state of the in state, and we can express p in using the creation operator for in states. Okay, a dagger P in. And we can do two similar things for the out state. Okay. And using the time evolution for phi, we have just obtained phi x to u infinity 0 phi in x u x0 minus infinity. We can easily obtain the relation between a and a, the relation between the a out and a in. Yeah, out. It's just a very simple definition. U positive infinity minus infinity. Okay, and the same applies for creation operator minus infinity, positive infinity, a dagger p in minus infinity. Okay, yeah, and generally relation between the out state and the in states, alpha out. This alpha can be anything. Okay, positive u minus infinity, positive infinity, alpha in. Okay, so much for this. And using these in and out states, actually we can we can express any so-called what? Yeah, so any transition amplitude q. Yeah, q and p. We can express this one using the in and out states. So we only yeah, q1. The general expressions, the most general expressions are q1, q2, out, p1, 2, in. Yeah, is the general expression for the transmission amplitude, and actually we can using this amplitude to obtain any observable quantity. Yeah, in our theory. Well, the textbook have discussed something about the decay rate and the cross section, but I think they are a little boring, and everyone can just read it. We just need to know we can construct any observable quantities from such an transmitted amplitude based on in and out states, and then that's enough. Okay, so the next question is how can we compute it? And so I think it's a very important formula we must introduce, which is the LSD reduction formula. Formulas. Okay. First, we consider the most simple case, for single particle, for one particle, Q out, Q in, and not P in. Okay. How can we compute it? Well, we just try to expand it using the annihilation and creation operator for in and out states. Out a dagger P in 0 in. And then using the expression for annihilation and creation operator we have obtained before. Let me check where is it. Yes, here, these two. Using this one, using these two, we can expand such an A dagger and obtain minus I is 3x. E minus IPX Q out I in X plus IP in X 0 in. Okay, notice that this pi in and phi in are just the limit for x0 tends to minus infinity pi and phi. Okay, so how can we proceed? Well, now we use a trick to perform such a limit. The trick. Here is a trick. Using the following identity tends to minus infinity f x0 because it equals limit positive infinity f x0 and minus infinity to positive infinity dx0 partial x0 fx0. Okay, it's just a no. How can we? Okay, use the wrong. Let me write it again. Limit. I don't like the new version of notability. Fx0 equals to limit 0 tends to positive infinity. Okay. It's just a identity which can be checked very easily. And notice that when we use such a when we use this first term in such a limit, we actually obtain the a dagger out operator. In the first in the first line of these equations. So actually this one, no, this one equals to Q out a dagger P out 0 in, and combine them, we'll obtain Q out P in equals 0 out dagger. No dagger. Okay. AQ out dagger P in 0 in plus plus I E4x partial x0 E minus IPX Q out pi x plus IEP phi x 0 in. Okay, notice the first term. Notice the first term. Yeah, the first term here. Actually, it's just 2 pi to 3 power 2 EP delta P minus Q. And actually, it doesn't contain any interaction term. So in our it will not affect the calculation of our transmission amplitude. So we can just drop it. Okay. So after we have dropped such irrelevant terms, we have Q out P in. This dot means we have dropped that irrelevant terms. We still use the old copy paste. Okay, it's still useful. Okay, great. Okay, so we obtain such an expression, and we can just how can we proceed? We can just perform such a time derivation to all the terms later, such as e minus ipx, pi x, and phi x, and using this on-shell relation p0 square equals to m square as momentum p square, we can finally obtain Q out P in. Let me check the top. Okay. Equals to, notice this dot, okay. Okay. E minus IPX Laplace x. This is just another expression for partial square x. M square Q out phi x 0 in. Okay, we have obtained this one. And we can repeat the same procedure for the Q out states. That's the naive next step. Repeat everything for its Q out. However, if we do it, we will obtain something like this. Q out P in equals to I minus IPX x M square. Yeah. 0 out. Okay. Q in x. Y0 P I Q Y. IQY 0 out IY minus IEQ phi Y x 0 in. Yeah. Okay, right. Now we encounter a problem because the ideal case that if this annihilation operator located in the right of the phi x, the first term will just vanish. However, it's not the case, and we don't know the commutator relation between these two operators. We don't know this one, so the first term doesn't vanish. How do we deal with such a problem? And so we use another trick called the time-ordered product. Another trick. Time-ordered or T-ordered product. Okay, the definition is below. T, T, A, T, B, T prime equals to theta T minus T prime. AT BT prime plus theta T prime minus T BT prime AT. And theta is the function defined 1, 0, T larger than T prime, T less than T prime. Yeah. So we're using such a time-ordered product and just go one step back to our repeated procedure for the Q out state. Notice that this formula, this term, I out y minus I in Q I out y. Okay, phi x actually equals to the corresponding time product 0 to infinity time product capital T phi y minus a eq phi y phi x. Okay, yeah, phi x. Why we can just add such a time product? Because obviously this t y0 tends to positive infinity. It will definitely larger than x0. So we can of course add such a time product, and it will affect nothing. Okay, so using this time product, we actually obtain the following expression. Actually, just to make a time product, making the make the right term of this one just as the corresponding time product. I rewrite it. P in it equals for x minus IPX. The x as m square out state. Notice that the phi x is located to the left of the a q in, because under the time product, this one obviously has the later time than this one, than the second term, the AQ in operator. So under the time product, it just it just changes the location we want. And yeah. Wait, and I think no. Yeah, and this time just vanished. This time just vanished. Yeah, and the second term is I d4y partial y0 iqy 0 out. And everything we have right before. Okay, 0 in T, yeah, with a T product. Okay, and for the second term, we just perform this time derivation. Just perform this partial y0, and we can obtain the final expression Q out P in equals to I square y e qy minus px lambda x as m square times lambda y as m square 0 out time orders phi x phi y 0 in states. That's the final expression of our LSC reduction formula for a single particle state. And it can also be easily generalized to the n particle states, such as generalize it to the n particle states. 1 Qn out P1 PM in just the IM plus n product I from 1 to M D4 xi E minus I pi xi. Notice this I means the number of the particle. Okay, it's not the it doesn't mean the space of it doesn't mean space. It's different from the x1, x2, x3, x0 in the four vector. Is we use a different meaning here. Okay, so lambda xi plus m square times product from j equals to 1 to n d4 yj ei qj xj lambda yj plus m square times 0 out state time ordered phi x1 phi xm phi y1 phi ym in states. And that's the final expression for the complete LSD formula for the interacting scalar field. Okay. Okay, so much for this. That's all the content I prepared for today's seminar. Okay, only one person here. Fine. Stop recording.